Thank you. Hello, I'm Sifis Lagouvardos. I'm a research engineer at Dedaub, and in this talk I'll give some information and insights about our tooling, static analysis mainly, but others as well, that we've been using on the Ethereum and Phantom blockchains to find real-life vulnerabilities. So I work at Dedaub, which is a security company that's been on the space for a few years now. The company's founders, Neville Grech and Yannis Maragdakis, have an academic background with many years of experience in static analysis. And many others on the team as well have been working on academia. I personally have been working on Ethereum tooling for 4 years, and most of this work has been on our decompiler pipeline and analysis pipeline, which have some shared bits. Okay, so our research and technology, as I said, is in static analysis. And what we do in static analysis is we try to create a model of all possible program behaviors, which, of course, is not always possible, but let's say that that's the goal. And when designing static analysis, we need to keep a very clear balance on 3 things. The first one is scalability, which is very important because you want to be able to analyze as many programs as possible. The second one is completeness. So you want to be able to model as many program behaviors as you can in order to catch as many bugs as possible. And the third one is precision. So you want to have very precise results in order not to burden the people that have to go through the reports that your program analyzers make with useless stuff, which in turn makes them not want to use your tools. So in our work, we use declarative program analysis, meaning that our programs are defined as as thousands of logical rules, which allows us to, in many cases, express some tough problems in a small and readable manner and make use of modern runtimes to speed up our analysis process. Okay, lots of the work I'll present here today is deployed on our contract-focused Blockchain Explorer contract library, which is available at that link. And we'll also have a demo here today. The basis of contract library, like when it was built, it was to expose our decompiler to the world. And after that, we've added a lot more features that are common to other blockchain explorers, but also others that are not found elsewhere. So the first thing I want to focus here today is the compilation. And in our case, we use the GigaHorse framework. The GigaHorse is an open source framework that we've been developing for many years now. And it's a vital part of our whole pipeline. So I'll try to not make this talk too technical, but it will have some technical information. So we'll start with a simple example. And this example is, it has a single storage, it's a solidity smart contract, first of all. It has a single storage variable, a constructor, which sets that owner variable to the message sender, and a guarded external method that allows the owner to withdraw funds. Now, what we analyze, we don't analyze the source. We analyze the runtime EVM bytecode. And this bytecode doesn't have the constructor information in there. So this is only, the constructor is only used when the contract is initialized. And in our simple example, it will have 2 external methods. The one will be the getter for the owner field, and the other the guarded method that is defined. Now, when we compile it and we get the runtime bytecode, we get something like this. which can be very easily disassembled to something like that. And so this is EVM bytecode in the assembled form, and we can see a few things. First of all, it's a stack-based virtual machine, meaning that in order to understand what variables or values these statements operate on, you need to model the stack instructions, which is it's not easy at all for humans, and it's not easy for static analyzers as well. So what we need to do is take this bytecode and elevate it to a higher level of abstraction. And a few other things I'd like to mention is that the contract has a single entry point, meaning that there are no concepts of public or private functions, and all of these are implemented using low-level instructions, a sequence of instructions, and we have heuristics to detect all that. And another important point is that, first of all, something you need to know is that these orange statement identifiers are the beginnings of what we call the basic blocks. And the basic blocks are sequences of statements that will always be executed one after another. And something you can see that on the basic blocks we've highlighted on the right is that in many cases, let's say the second basic block, you can see that you push a statement identifier and then you jump to it. So looking at this basic block in isolation, you can see where the next one is. But if you go below that, it's a basic block where you cannot see, if you look at it in isolation, what the next one will be. And this is very important because this is where static analysis comes in. These blocks are used all over the place, they are shared, and we use static analysis to create a model of all the possible behaviors in order to be able to decompile that. And when we do decompile it, we get something like that, which, as you can see, is more high level. So we have the edges between the blocks, like the control flow is recovered. And what we also have is we've resolved these operations to the variables that they use, or constants, which allows us to better understand the program. However, so this is the code for the owner getter. So this code just fetches a storage variable. But as you can see, it still has lots of low-level information that is required for compilers to put on to support high-level features in a very low-level virtual machine like Solidity. So what we do after that is we have libraries that run on top of this and produce high-level facts. And in this case, the facts will look like that. So we removed lots of the shifting and masking operations, and we see that, for example, variable 125 loads a storage variable that takes part of storage slot 0. And then we return that, which was previously done through a series of memory stores and memory loads. And this is the level at which our analysis operates on. So we have the decompilation, we have a normalized form which is useful for analysis, but we also have many libraries that help us get lots of high-level inferences, so we don't need to care too much about the low-level intricacies of the VM. Of course, we do care about them, and we have to model them at every stage. And using that form, we can also get a source-like decompilation output. And as you can see, in this case, it looks very close to what's in the original source. Of course, it's a very simple program. And in the bottom right, what you can see is also the function dispatch code, which is not present in the original source, but we keep it for completeness. So it's how the program decides which function is actually being called. So of course, the biggest use of this pipeline our security analysis. And most of our analyses are built on top of our symbolic value flow engine, analysis engine, so the symbolic engine. And you can think of it as a technique that combines the good things about static analysis, the fact that it's fast, the fact that it covers many program behaviors, tries to cover most of them, and the precision enhancements that symbolic execution will give you. And in this talk, I focus on a specific subset of clients, which we found to be very useful, and they can be generalized as in the form of a sensitive operation that can be reached by an unprivileged caller. So this allows us to express things like a sensitive operation could be anything, like an ERC20 transfer from, a delegate call, a self-destruct, or many many sensitive calls to DeFi protocols. So it's a very expandable framework. And let's see an example of such a vulnerability. So this is a pattern that used to be common in yield aggregators like a few years ago. Basically, they'd have a harvest or rebalance function that was callable by anyone, and it allowed them to withdraw rewards, the rewards that the token, that the contract, like the specific strategy, had accumulated on another DeFi protocol, swap them to the base token, let's say, and deposit them again to that other DeFi protocol to continue getting yield from them. So this is a very simple pattern, and they thought it would be all right to just let anyone call it. However, there's an issue with that, and that issue is specifically because they do not specify what the minimum amount they need to get out of this swap is, which basically allows any other contract or MEV bot to tilt the pool essentially first, influence it on their benefit by adding a lot of, by swapping lots of A tokens to that pool, leaving this, the swap of this contract to get very little benefit from the swap it does in this function, and then swapping the original tokens they got back to get like what this would have gotten, essentially stealing its profit. Now, this is a complex case, and something that's interesting and brings me to my next point is that static analysis for that will give you this contract if like you have the specific client for it, but it will not tell you when the conditions of this to be vulnerable are met. So this is where we need our whole infrastructure. So we start from static analysis, and we move on to something that contains a lot of information about the blockchain's state and past transactions. So this information about the blockchain state needs to be processed, basically. So it can be information about the token balances and allowances between contracts and EOAs, let's say. It could be proxy-related data. So this proxy uses that implementation, and that implements that particular contract proxy protocol, let's say. And also we need information about the contract storage. And we've also found that information on past transactions can be useful because, let's say, in the proxy case, you want to see that a proxy hasn't been initialized. So how we do that, one way to do it is to check through past transactions. Okay, so this brings me to our next, our second product other than Contract Library, which is Watchdog. It includes all the features of Contract Library, but it's security-oriented. So it allows people to define their own protocols or upload in development code to it, our static analysis run on top of that, and security researchers and auditors can inspect them. And it allows you to combine, or our researchers to combine the results of a static analysis and their inspection, so we can find out what's really vulnerable statically by looking at the code, and combine that with static information to find real-life vulnerabilities in the wild. And it also has a lot of freedom regarding transaction information. Basically, it allows, we developed an SQL-like query language to allow people to create their own triggers for transactions, to set interesting events, like to say if this function is called under this condition by, this function of my protocol is called under some condition, trigger it and send me a notification. And over the past 2.5 years, we've used this system to perform a number of high-profile vulnerability disclosures. In total, there are 10 disclosures, some of which, let's say, are swaps, like the one I showed you. Others could be defined on various things, like reachable transfer froms, or delegate calls, or vulnerabilities regarding certain proxy patterns. And also other, like we've recently had some very high-profile ones. Not all of them were aided by static analysis, but most of them were. And as you can see, yeah, these vulnerabilities were in major protocols, and they got a lot of high-level, a lot of rewards for finding them and reporting them. Some other uses of GigaHorse that I wanted to mention are impact studies. So we've been approached by the Ethereum Foundation a few times to assess the impact of certain proposed changes to the EVM semantics to all, or as many as we can, but mostly all, deployed contracts on the Ethereum mainnet. Basically, we get the pattern. They say that this could break some smaller or bigger things, and we use static analysis to identify contracts that have patterns that could potentially be affected by that, by this change. And then we also use dynamic information to verify that and to assess the impact that way as well. Perhaps the most interesting, certainly the most relevant one, was the recent study we did about the removal of self-destruct, which 2 weeks ago was presented to the core developers meeting and helped them take the decision to accept EIP 6780 to the next hard fork and change the semantics of self-destruct, essentially only allowing it to work if the contract is created and deleted in the same transaction. So another interesting use I wanted to mention is that we recently used GigaHorse to identify a Solidity compiler bug. This compiler bug was fixed in version 0.8.19, and the description of the bug is the following. Basically, as I mentioned in the beginning of the talk, contract that's reachable through in the contracts constructor doesn't belong to the runtime bytecode because it's useless there. So if the bug was that if library functions especially were called only on the constructor, they would still end up being part of the bytecode. And for some proxy patterns, this was catastrophic. Essentially, for example, for diamond proxies, it would cause over 90% of the deployed code to be dead code. And the interesting thing that we detected this when trying to actually debug our tool, because we noticed that we have cases where a very high number of dead blocks is reported, so I thought something is up, like this isn't correct. And we went in and found that it's actually a bug in the compiler. Okay, so thank you for your time. Now we'll do a quick demo of contract library, but feel free to check out the GigaHorse framework as well. It's available on GitHub. And so this is the front page of contract library, which is used as a contract-based blockchain explorer. And let's say you have some bytecode you want to decompile. So you click on the bottom, on the top right, you paste that bytecode in hexadecimal form, and you click decompile. Now, this had already been decompiled, otherwise it would enter a queue and finish in a couple of minutes. So as you can see, we entered that, and we recovered what looks like a Uniswap to pool. And as you can see, like our UI also indicates that this is deployed on the mainnet. It's a Uniswap v3 pool. So here you can see the decompiled code and other levels of abstraction with output. We output something that looks like YUL, which can allow for reuse of that code. The 3 address code I showed you earlier. So we can use that to go to the Uniswap v3 pool and find its deployment. Now, again, here we have the decompiled code that was the same as the previous one. You can go to its source as well. So it has the contract sources. Through that, we have an easy way to communicate with the contract's storage, read it, and also the mappings and other parts of that. And we also have lots of information about token-related things, like ERC20 balances on that, the balances of the contract. So as you can see, this has USDT and WETH, so it's a USDT to WETH pool. We also have the allowers of the contract, so which contracts or EOAs have given this money allowance to this contract allowance to transfer their money, and there are quite a few, as it's a Uniswap pool. We also have information about past transactions. And you can click on them and get an overview of the transaction in terms of token transfers, balances, and also the transaction trace. And we can also go back and quickly show some other ways to call that, to interface with its storage to read or write transactions. But yeah, if that's not easy right now, it's okay. I'm happy to take any questions. So no questions? Yes, please.
Hi. I think Dedaub is a great tool for reverse engineering. And so I have 2 questions about that. The first one is, your tool is path sensitive, right? So how to avoid path explosion? I mean, if there are too many code reviews, like some basic blocks.
So how do you avoid path?
Path sensitive, since your tool is path sensitive, right?
I'm sorry, I don't get the question.
For example, if there are some basic blocks which are reused multiple times,
Yes.
so there might be too many passes in the control flow graph, right?
Yeah, so what we use to help us with that, we use a program analysis technique that's called context sensitivity. So it's an abstraction where our kind of, the context sensitivity that we use basically tells you that every time you analyze a basic block, you try to remember certain things from its past, the past callers. Because we couldn't, let's say, remember all the past callers, so we have abstractions and heuristics that help us remembering these, and they allow us to differentiate the different uses of the same basic block in different contexts. And we also have some other small hacks to get around that, like if some block is used many times in a way that can make our analysis bad, we may sometimes clone it, let's say, in a few different places.
So basically, what I'm talking about is some heuristics try to avoid the pass explosion, right? This problem. Because it's a common problem in the program analysis field. If you try to build a concrete control flow graph, so, yeah.
Yeah, like the heuristics we have is that essentially what helps us in the development in the EVM bytecode, and especially in solidly produced code, to get a good control flow graph is that there is information about possible call sites, let's say, possible private functions, and we use that.
Okay.
We use this kind of heuristics. Like we have a research paper that explains that in UPSLA 2022.
Okay. So
does that answer your question?
I think partially, I guess. We may have more discuss later, but I have a second question. So is that okay?
Yes.
Okay.
Like, if you want to, you can get back to first question and clarify it. Like, feel free to do so. We have time.
Okay, that's cool. So my second question is, because your tools relies on the symbolic execution, right? So as far as I know, it's very, it's very slow. For example, some other tools like MissReal or MissX, they use the symbolic execution globally. So the performance is not very good. So my question is, do you use it globally or just use it on demand?
So our analysis engine does not really use symbolic execution, but what we so first of all, like our whole pipeline, like we run it on everything that's deployed because it can scale very well. And what allows us to scale is first of all like the fact that we use static analysis essentially. So for decompilation, we get a coverage of like over 99% of deployed contracts, and everything is decompiled on our site. And for analysis, we don't always analyze everything because, you know, on the blockchain, there is lots of past contracts that are not used. So we don't analyze everything, but we analyze what's like used in the past few months constantly. So because we constantly improve the analysis, and yeah, static analysis and like the techniques we've developed, which may borrow some elements from symbolic execution. So basically, we try to have something close to a pointer analysis, but the values can be arbitrary expressions, and we keep like very deep path-sensitive information about where we were. So this is, so yeah, these kinds of techniques and the fact that we tune it a lot, like we work with the latest contracts to ensure that it runs. Helps us to be able to decompile and analyze most contracts.
Oh, okay. So basically, you have a prudence strategy, and use the historical transaction to do that.
Yes.
Okay. Okay.
To know which contracts are important to analyze, basically.
Okay, got you. Thank you.
Thank you for your questions.
Thank you for engaging with the audience, Sifis, and thank you for asking amazing questions. Please give it up for Sifis.
Thank you.